So I guess we can start. So the goal of today will be to I don't think we can finish this one, but at least we'll finish most of the thing about games in with complete information. So I would say this is the one of the most important chapter that for you, because a lot of application you would actually focus on complete information setup. The reason is being that it is easier to build it as a first round model because there's one way to do it in the complete information way, and there are many ways you can model in complete information. So that's why unless you think information is important for your model and that change a lot, otherwise I would recommend you build a model based on complete information, and then you can see that even in this particular context of complete information, it is already can be very complicated when you try to build a model. If you have multiple stage, many agents, then already the model can be very complicated to solve. So as I said, there were 80-something slides. I'm not expect to finish everything, but I think we can at least finish half of it, right? Or more than half. So we will start with very simple model where in each period of point of time, we have one player move, because this different from what we learned in topic 5, where players move simultaneously, right? And players simultaneously doesn't mean they have to be in the same time. It just they make decision without knowing other people, without knowing how other players decide what to do, right? So here, when we have sequential game or dynamic game, which means that one player move, the action will be known by the other, and before other make another decision, right? So there's the time is in not in the action, but rather the decision, right? And then at the end that they decide at the same time, right? The game is realized at the same time, but it's rather who knows what, right? When they make decision, right? If there's a spy, right? Then from one player to the other player, know how other player choose, then it can be even though if they decide simultaneously, then you can still model in this framework, right? So that would be the main idea behind this model. And then after that, we extend to the second set is we focus on the simultaneous move game, but they have multiple stage. And this is also more complicated model, and often that is a model for the supply chain, right? Say suppose firms in the upstream move first, and then firms in downstream move the same time, right? So that would be the thing we do. Or you can imagine corporate finance, like firms decide first, and then investor do the action, right? So that would be the time. Or the one who move first is long run players, and the moves in second stage are short run players, right? So that is also possible, right? Maybe bank decide how do they lend their money out, right? And the investor decide whether they trust the bank and keep the money in the bank, and so on and so forth. Okay. And after that, they will come to a first set of topic, which I think is a huge one, and then it's also a difficult one. It's called repeated game. It's saying that if the interaction is not end in one, but continuous many times, or even infinite many of time, what would we expect? One reason we want to do that is people tend to be more selfish when they only interact once, right? There's no collaboration in the future. They do selfish thing, but when experiment actually show that when people have to face the same decision over time, they may be able to sustain some collaboration. In particular, we want to understand the main game is called precedent dynamic, which we have seen last class, is the question would be, is it possible that players can sustain collaboration under repeated game, right? And the other thing is, under repeated game, is it possible to sustain or to observe something that is not an equilibrium in a stage game, right? So if something is not equilibrium, but because of the future interaction, can we do something better, right? So that is a present dilemma, right? Just you know the dominant solvable is both player defect. So the question is whether they can sustain the outcome that is not in the natural equilibrium, right? When you expect to repeat many times. Okay, so that is the repeated game, right? Is a implicit contract or the trust or institution, right? These are the problem that actually underlines here, right? If you know the recent Nobel Prize that award about institution, law, and norm, this kind of stuff is actually with the game, right? And right, one of the paper, right, the AC McGrew, right, the Ron written, right, is like why you have institution, right? Institution is there because of it's more difficult, costly to change, right? Because of the this is a kind of promise, right? You get irreversible action. If you do this and you change the rule, is very difficult, right? So that means that it's able to commit, right, to convince people to do things. But we try to see if we can talk about those points. The last will be somewhat we call price coordination. We will just apply the repeated game idea into a firm collusion. Okay, so that would be the main thing, right? So let's see the dynamic game of confirmation, right? And here we start with the most modest setup where players take turn to make decision, right? And then to recall that the static one, everyone make the same time, and the dynamic, the simplest one is every player make decision at different point of time. And the easiest one is talking about the sequential matching pennies model, right? And instead of both players showing their pennies at the same time, you just ask player one review first, and then player two decide what to review after looking at player one, right? Obviously, player two have substantial advantages here, right? Because he can choose after seeing what player one have done. So the first complication, actually, you will see it's easy for player two, right? Because he can decide afterward. But in terms of strategy, player two is actually way more complicated, right? It's easier for him to do, but he has to decide what to do in all possible scenarios. So instead of saying head or tail, right, he has to do the following. He has to decide head if player one show head, right? He can also have to decide whether to show head or tail if player one show tail. So instead of strategy, right, head or tail, he has to tell under the two possible scenario what might be the action. So the strategy set is instead of two element head or tail, you actually have a vector of having two element, right? Instead of just head or tail, you'll be head under if one player choose head, right? You head or tail. If tail, what it's going to do, right? So it's 2 by 2, right? It's 4 possible strategies of 2, right? So it will be this, right? So under all scenario. So it can be very complicated, right? Because suppose you are saying that if player one choose a number and after that player two choose a number, then it will be way more complicated, right? The cardinality expand a lot, right? So that has but anyway, the important part is have to specify all possible scenario. Okay. So why is the case? It's just like you say the strategy has to be a book how it's being played, even though the player is gone, right? The player 2 would tell a machine or someone delegate to him or her, in the sense that if he's away, go to the washroom, the game would proceed as what is being given, right? So there's no problem. And you may ask, hey, come on, if it is dominant strategy for player 1 to choose head, say, suppose, then why I have to specify what player 2 if tail is being chosen? The reason is being that you have to check, right? Whether player, what are these strategies in equilibrium? We need to check that. It will be well clear later. This is very important because sometimes that, I mean, some paper, in fact, even published, they didn't specify that, and that can lead to some problem of equilibrium. So so that is some issue there. So how we would define an extensive form game? Usually this is not defined formally in your paper, but you would do it informally. Okay, and remember how we define a strategic form game or normal form game is player, strategy set, and payoff function, right? 3 things. So now we have much more because it has to depend on what can be done. Okay, so first one, the player set n, that's no problem. The second one would be the history, set of possible history. So what might have happened, right? Because this time is a matter, right? So what are the contingency? What can be there? It will be the history, set of history, right? Maybe in this case, head being chosen by player 1 or tail being chosen is the history, and nothing is being chosen out of history. Okay, and so far what the outcome, that is history. Okay, and because here we have to decide who move, right? And only allow one guy move, so I have to say Z will be the set of terminal history, actually the outcome of, and you have to tell for this non-terminal history who is going to move, right? In the case of example, we have player 1 is the first guy who moved, right? That means that the P of the null history mapped to player 1, right? And if it depends on tail or head, you will map to a player, right? And what can be done, right? Can be terminal history, right? So that's why a strategy is not just a set, but a set depend on history, right? We don't use strategy instead of action because strategy is have to specify action for all possible history that player have to move, right? So that would become A, and history will be just all the action have done in the past, right? So action will be all action have been done in the past, and payoff will be depend on the end, right? What all people have chosen and then map to the payoff. So that would be a complete description, and usually we don't do that, right? Because it will be too tedious. So some terminology before we make sense of these with some example when we make sense of those. Okay, so strategy will be saying for all, as I said, for all history that player have to move, what are the what he can do, right? In the right, that would be that case. And the strategy profile will be set of strategy for all players. Okay, and in this game there's no restriction to define what's Nash equilibrium, right? The same as we've seen in the last class before, right? It's just a strategy profile such that no one will deviate from that. Okay, so that is well defined, right? Even though we allow people to move at different point of time, it's still fine, right? It's a well-defined concept. So player 1 move first and player 2 move second doesn't invalidate this Nash equilibrium. Okay, but let's see the example to make sense all the terminology, because the first time you see this, that would be crazy. Okay, the first one we have 2 players, right? You can say the The player set is 1 and 2 because 2 players. And the history, because we start from nothing, so the first history is now history. Okay, you start to now, no one move. And player 1 can choose head or tail. All right. So the history can be either head or tail, depending on what player 1 is doing. Okay. And time 2 is a terminal note, right? Because after that the game is over, right? So after head or tail, right? If under head, if player 1 choose head, the history become head. If tail is head, then tail. Okay. And if under tail, if player 2 choose head, they will tail head. If player 2 choose tail, will be tail tail. So that means that the terminal notes are head, tail, head, and tail, tail. Okay. And the set of strategy will include everything from the beginning. You have an empty set. Okay. You have which is the time 1. Under head or tail is referred to time 2. Sorry, time 1. Right. There's time 0, time 1, and time 2. Right. So it's combination of all possible moves, right, with the set of history. Okay. So because it's different point of time, right, and that possible people can move, right. This is the time where player 1 move. This is time this is time player 2 can move, right. After player 1 move, this is time for player 2, and these are the case where everyone have moved already, right. So why we care about this history? Because history can tell us who can move, right? Under the now, player 1 move, this player function. After XCT, and then player 2 move, right? And available action will be what is available, right? No matter the first player 1 can choose head or tail, right? And player 2, regardless of head or tail, he can also choose head or tail. So that's no different, right? Because this potential can be different. Okay. So, but in here, a player 2 actually has the choice is no different, right? And payoff will be look at the terminal note or the payoff. Okay. Of course, this looks crazy. I mean, to do it formally, but usually it's more often you see this undergrad, right? This is a tree to describe everything. I mean, usually either we describe it verbally, okay, or you do it in tree, okay. But do note that everything is in the formal description is on the tree, right? Just like the matrix, right? We have a normal form game. We can matrix is a complete representation, and this is also complete representation, right? And you can see the full circle are all non-terminal nodes, and the hollow circle are all terminal nodes, right? You have C with 2 players, right? And the number actually represent which player can move at which node, right? And the who can move is also the payoff, means the payoff function, P, right? And the strategy is represented by the 3 branches. And more the name you can do, right? The action function. And the payoff function at the end is put in here, right? So everything is fully described in the tree, right? So you don't miss anything from the tree. So of course, you can collect all the names that become the player set, right? So basically on the tree, right, you can tell everything we want to say, right? So that means that as long as you can write a tree, then it's already a full description. So what a strategy in this particular case, right? The strategy is, as I said, right, because player 1 under the now history is only choose head or tail. But player 2 have to specify all the action he can take for all history, right? The history he can take action is head and tail being chosen by player 1, right? Then he has to say, under player 1 choose head, what he's going to do. Tail choose what to do, right? So he has to specify that, okay? The strategy is independent of what player 1 will actually do, right? So that's why, say, H and T will be player 2 will choose head if player 1 choose tail, right? Choose head. If T will be player 2 choose T, okay? And so you can see the outcome is rather complicated, right? Because there will be 4 different choices for player 2 and 2 different choices of player 1. So indeed, the outcome under a combination of this strategy profile, and these are all the outcomes. Okay, and Nash equilibrium involves checking every X strategy, would any player want to deviate? Right, so that would be the way to check Nash equilibrium. Right, for example, if you want to check whether, right, player 2 want to deviate, right, you have to check whether this, if they want to check this outcome is a equilibrium, you need to check whether this player 2 will deviate this, and this, right? And in this scenario, you have to check this, right? Because you have to hold player 1 strategy constant, you check among this, right? And if this is the equilibrium, you check all here, right? But you don't need to check, you don't need to compare the above. So it's not comparing everything, right? You know already from the from there, right? So it's just holding one guy strategy in check, right? So suppose you want to check this one, right? You check the first one and the 5th one as well, right? So check player 1. Is that clear? Let me say that again. So to check H, is it a Nash equilibrium? First, you check whether player 1 will deviate, which means that you check H divided L, compare these 2 guys, and that's it. Player 2 is to check player 1 hold the H, player 2 want to deviate to this 4. Okay, if none, then this is a Nash equilibrium. Okay, so to check for every single strategy profile, this is how you would do for Nash equilibrium. Okay. And the question would be, okay, Nash equilibrium is well defined, right? And it can be shown it always exists, right? Because we have shown that it always exists, right? They say because the same as before, right? There's nothing new from this, right? So the existence is already almost guaranteed, right? Because you, in the finite game, finite pair, Nash prove that always exists equilibrium, right? In the mixed strategy, right? If everything is nice, then there's no problem. So the question would be, in this context, is Nash equilibrium a good prediction? The answer is no, unfortunately. And if you know this game, right? And if you go back to the idea of this game, right? The game was said if the coins shown are the same, player 2 wins, right? If had player 1 get $1, tell player 1 get $1. If different, then player 1 wins, right? So player 2 obviously knowing what player 1 do, have a winning strategy, right? Always look the different coin, right? Under same coin, right? Under head, he will do head, right? Under tail, he will do tail because guarantee winning, right? So that means that, okay, and mixed any is not prediction because no one mix, okay? And also, there will be an any that something that is not good, right? Because later you will see that and Nash equilibrium will not be an appropriate solution. Okay. As we said, this is dominant strategy, right? No matter what you do, this dominant strategy, right? So checking other thing would be inappropriate, right? Because the equilibrium that, say, player 1 choose H, player 2 choose H, but player 2 choose head, okay, right? This is also okay, right? But this is not, it is a Nash equilibrium, but it's not a reasonable prediction. Let me repeat. Player 1 choose head, okay, and player 2 choose head, underhead, choose head, undertail, which means that no matter what, he choose head. Okay, this is a Nash equilibrium. You can check, right? Because player one would not change, right? Maybe or maybe not, right? And well, in that case, player one will change, right? In that case, right? So in this particular case, or in particular cases, they would be coincide because Bob necessarily. Okay. But let's see this game. You will see Nash equilibrium is a poor prediction. Okay. So in this particular case, okay, this is a common case when we talk about the prediction game. Where two firms, the new guy can decide to be go in or stay out. Okay. And second stage, the incumbent decide to fight, accommodate. Okay. If it's not in, then he just enjoy monopoly, right? So it means that if there's no entry, entrant don't earn any money. Otherwise, incumbent earn $2. If accommodate means that they don't fight, the incumbent get $1. They equally split the market, right? If they engage in a price war, then they're fighting. The new guy comes in, is more costly, -3 and then -1. Okay, for the incumbent. So these numbers are make up, but you can see student B.A. It's not crucial. So if you write this in the table form, right, the normal form, right, then it will be if out, no matter what you do is 0 or 2, right, it doesn't really matter, right? If in, then will be -1 and 1, right? So that would be the idea. So if you check this 4 outcomes, you will see out and fight is a Nash equilibrium. Why? Because player 1 don't want to deviate. Player 2 don't want to deviate, so this is Nash equilibrium. And this is also Nash equilibrium. Player 1 don't want to deviate. Player 2 don't want to deviate, right? So that with 2 Nash equilibrium, okay? And the idea is that, well, is these 2 outcomes are equally probable, right? The question is, if this is in, right, actually do I want to fight, right? If this is fight, right, actually payoff is very low, -1, right? Rather, actually, he would try not to fight, right? He just saying that if you come, I will fight you. So you don't come in equilibrium, right? Just being crazy, right? Means, right? It's not what we say, not credible, right? Right? Then it's not clear why this would work, right? If that might be an empty threat. Okay, it's saying that if it come, right, I will do crazy, right? But this is not crazy, then not clear, right? Just like what happened in recent Russia, right? It said if you attack me, I will make a nuclear bomb. Is it credible? I don't know, but if they believe it, not clear, right? And it seems like that's like when a man and a woman engage in a fight, right? And the woman said, if you don't come back tonight, I jump off, right? Something like that, right? But right? And usually it doesn't really happen, right? Because this is not rational for the woman to jump off the building, right? So the man keeps going out and play, right? So this is something like this happen, right? So of course, there's a lot of literature tell you how to make it credible, right? How to make your threat credible. But that's the idea, right? If you, right? So that is the idea. So here is the idea here, right? Look at the game tree, right? And what would be the solution concept that we should use is have to be more strict. We will use the concept from operation research called parallel induction. Okay. And backward induction involves saying, okay, why don't we look at the very last point of time where the incumbent have to choose what to do? In that case, his complaint fight or accommodate. In that case, accommodate would be the only rational thing to do. Okay? And that means that we can ignore the fight. Okay? And that means that the entrant only decide whether he would do out, he gets 0, or in, you get 1, because this will not be realized, right? If we believe that the incumbent is normal, he's not crazy, right? If he's not crazy, then it will never be chosen, right? Dominant is like strictly dominated, right? So that means that he would be thinking, okay, either it's out and in with accommodate, right? This will be chosen. So in that case, that will be the prediction, right? So that would be the only possible prediction. Okay. So, but then the question is, this is very natural, right? You would think about is you saw from the backward, if everyone is normal, then this is a prediction. But of course, I mean, that's why people tend to act like crazy, right? Just like when some people in China want to get the salary back from the employer, right? They may carry bombs, carry a knife, right? Or if they don't give money, I kill myself, right? There's something like that, right? Or when there's a fight between some Shandong or Dongbei people, right? They bring their knife, and then before they fight, they cut himself first, and then right, the soul is very strong. You don't want to deal with me because I'm crazy, right? Or like the chimpanzee, right? When they fight, why do they do that, right? Why do they pound their chest, right? Make them hurt? No use, right? But by pounding his or her chest, then become very strong, right? Become right? Absolutely no reason. But that is how the backward induction apply. But how does backward induction related to Nash equilibrium, right? The question is, right? Is it any way that related to that? Okay. It is called as the Shelton proof, that is called subgame perfect equilibrium, or sometimes called subgame perfect Nash equilibrium. It's Nash equilibrium, but we require it's a subgame perfect. So what is subgame perfect? Means that we first look for all the Nash equilibrium, and we also require, this is also a Nash equilibrium in all subgame. And what subgame? Subgame means that it can be considered a game by itself, or you can imagine that I have a tree here. Okay, at this point of time, okay, if from this point I forget what happened in the past. Okay, and is it a game by itself? Okay, basically what I do is I set the history here to 0, to empty set. Is it a well-defined game? Okay, from that on, it's a game. If yes, then it's a subgame. Okay, and in this subgame, as a one-person game, we can look at the Nash equilibrium. All right, and we require that if I say the equilibrium of the whole game, it must be the case that this part is also a Nash equilibrium in this subgame. That is called subgame perfect Nash equilibrium. You require Nash equilibrium in every subgame. Okay, so basically it's a combination of backward induction and Nash equilibrium. Okay, and right, so that is how we solve the problem. Okay, and turn out this is the same thing, right? If you solve the method by backward induction, it's same as finding all the subgame perfect Nash equilibrium. So there looks like different concept, right? Because you can solve the game by backward induction, right? Another way is to look at all subgame, you solve Nash equilibrium, and you find all the intercept, right? And turn out to be the same thing. So that's why we use interchangeably. We can look at the last game and solve backward, or we can look at all subgame, solve all the Nash equilibrium in every single subgame, and look at the intercept, that will be the same answer. Does it make sense? So let me repeat the statement here. So you can use parallel induction, where you solve this game first, and this become this outcome, and put it back here, become 1-1, you solve this game, either 0-2 and 1-1, right? So this parallel induction method. The other way, yes. The same, just go one step by step there, right? So the other way is consider the subgame perfect idea. This is one subgame, you solve it, and solve the whole game, which we already seen it, okay? So in a big game, these are two equilibrium, but you look at a smaller game, this is only these two things, right? Only in is there, so only this game. So it's only here. So the intersection is only this guy. Is that clear? So I hope it's clear, right? Because in the subgame, where only player to move is only the case entrance and desire, so it's gone. So in the subgame, only this is available. Okay, and player one obviously will choose this guy. Okay? This is the Nash equilibrium subgame where the incumbent has to move. And in the whole game, these are two Nash equilibrium. And subgame perfect means that I require Nash equilibrium in every subgame. So it is only this is the intercept. Yes. Yeah, any SPNE is NE in every subgame. Has to be. So the orange is the original NE in the original game. And in the subgame, only look at the blue one, only the red is the case. So that is how you solve. But we also said that actually have been proven it is same as you solve this game in the following way. So look at this subgame. The optimal is this guy, right? So what you do is you forget about this subgame, replace the outcome with 1-1. And look at this again. This is the only outcome. So this is the parallel induction solving. Okay, and we say that actually can be proven these two methods are the same. And that's why we always use the parallel induction as a way to solve, because it's easier, right? You don't have to worry about the intersect of all the subgames, right? So that's much simple. So that's why I look at this. We always use parallel induction. Okay, and parallel induction is possible if you have finite number of period, because you can go to the last period and do parallel induction. But there's no last period when you have infinite game, right? So that's why we still have to define subgame perfect, right? In that way, because parallel induction is only feasible when there's a final period to do things. But when you go with the game, when you go to more games, complicated one is infinite game, then you can't really have that, right? Because there's no last period to go back, right? And we talk about with the game that often we see is we can't do that. Then that means that we have to have the idea of subgame perfect, right? Because it's not defined with infinite game. So they're different. The only equivalent when there's a finite horizon. Is that clear? So probably you would ask, what is infinite game here? One of the famous games is a bargaining game. So the famous one is like, I have one, you and I are going to divide a cake, okay? And I make a proposal, and how to divide it. If you accept, the cake will divide as we agree. If you reject, the cake will shrink a little bit, maybe by delta fraction. So because maybe ice cream cake, right? It's melt a little bit. And then you propose again, it's to you to propose. And if you propose, if you agree, then they divide accordingly. But if I reject, then you will shrink, and it will be my turn to propose. It's called take alternating offer. I bring an offer to divide, you accept, then you divide it as so. Otherwise, the cake has shrunk a little bit, and then you propose again, and then potentially you can keep forever. Okay, there's no time limit, right? Can go to infinity. Okay, but anyway, then you can not do barrel induction. Okay, for that one. So I guess it's good to try to work on this one because it's important for understand this one. Please don't look at the answer. Try to, before pipping, right? Pipping is not good for you. So let's look at this. What are the strategy set for player one? For player two, how many sub-games are there? What is the set of SP and E, right? So let's try to work it out. I give you 3 minutes to work it out, and then we discuss it and the break. Okay? Please try to work it out. Don't look at the answer, please. Otherwise, you are not helping yourself. I mean, easy to check the answer anyway. Don't look at the answer. It's very tempting, but I hope you don't. So I hope you don't keep. So what is strategy for player one? Player one only move here, so just A and B, right? So just I'm not peeping as well, so I do it with you. I didn't peep before I come to the class, so we are at the same level. So player one is A and B, so we just write A, B is a set, so you have a curly bracket here. A and B, okay? Remember, strategy is to be the what you can do for all possible history, okay? Player two can move according to history, either A or B, right? Have to specify under A, C, D being chosen, under B, F and G being chosen. So it's a 2-element there. It's a function, right? So each is C, D, and E, okay? And cross product of F and G, right? So totally, actually, the strategy is actually have a 6 possible choice: CF, CG, DF, DG, EF, EG. Is that clear? 6 choice. Okay. Have to be very careful. Have a 6 element there, not 5, it's 6. Now, what are the set of SPEs, right? So we will use what we call backward induction. Okay. We're trying to see all the subgame. Okay. So look at the E's subgame first, the right-hand side, F and G. Okay. Look at F and G, which one is better? In this particular case, G is certainly better. All right. So this means that G, in this subgame, this is the only Nash equilibrium here, so we only care about 1. And look at the second one. What are the choice between is 2, -1, and 2? So either this guy or this guy is a Nash equilibrium. Okay. So there are 2 scenarios. So backward induction have to do 2 different scenarios, right? Because under this scenario, G is being under the strategy, CG is chosen. The game is either these 2, right? Under EG chosen, the game is all following this one. Okay. So we look at the case. The backward induction have to do twice. Okay. First is under CG. Okay. Under CG. Okay. Under CG, what will be player 1 doing? Under CG, player 1 is between A or B. A or B will give 1. Doesn't really matter, right? Player 1 is indifferent. So A is equilibrium, B is equilibrium. So it will be ACG is the first equilibrium. BCG is also the second equilibrium. Right? Because under CG, 1 is indifferent, right? Say. Now the other one is EG, right? Will be the choice. So under EG, you do backward induction. Under EG, player 1 is looking at 0 under A, 1 under B. So clear what is going to be chosen is B. Right? So we have, you can see we have 3 subgame, perfect Nash equilibrium. We solve it by backward induction. Right? So although I guess many of you have know it, but we have to define formally here to make sure that you don't miss anything. Because it's very easy to miss something when you actually write a model. Right? When you actually write a model, you will be tempting to say, okay, A is dominant strategy. We don't want to care about this and forget about those. Right? That's very often. Right? You would omit that. Right? You make some assumption there. Sometimes may be reasonable, may not be reasonable. Right? Maybe you would not define, say, in the early game, someone exit the market and then nothing related to them. Right? But it is possible that they may come back. Right? Depends on scenario. So you have to be very careful how you specify the game. Okay. Is that clear? Okay. This is I think I have elaborated the answer at the second page, I think. Yes, it's there. So I hope this is clear what we're doing. So after the break, we will talk about, we have C backward induction is very nice. Okay. After break, we'll talk about this game we call centerpiece game. And this is an experiment actually shown that backward induction is problematic, especially for complicated game. Okay. So if you do experiment, you will see this is a problematic, and you will see a human more or less what we call bounded rational, or people fail to see things. But you can see even for us, even for me, it's very difficult to see the answer. Right? What's appropriate prediction? I don't know. But anyway, this is a good, you can look around, look at this and see what with the outcome you would guess. But let's see. Okay. So let's have a break of 15 minutes and we come back at 13:35 and then we can discuss this game. 15 minutes break. Feel free to go to the washroom, drink water or what. then your blood will a little bit circulate. Whereas otherwise this movement going to be stuffy. So let's get back. So the idea here is like the following. Okay. So basically we start with $4 on the table. Okay. And player one decide whether to stop or continue. If player one stop, he will get $2 more than the opponent. So start with $4. If player one stop, he will get $3 because he will get $2 more. The other guy get $1. And if player one decide to continue, there will be $6 in the pot, right? Where if player two stop the process, player two will get $4. Player one will get $2 because every time continue get $2 more. And after that, if $6 is done and $8, right, so on and so forth, then who said to stop, then we get $2 more. Is that okay? So you will grow $2 per each time you continue, and the player who stop will get $2 more. Okay, and then oh, I think this maybe this should be 7-7 or 8-6 because that doesn't really matter anyway. But I think I have to check how to define the last one, but doesn't really matter anyway. So the question would be like, okay, what will be the sub game? Because actually you can see from the backward you get 1, 2, 3, 4, 5, 6 sub game, including the whole game. So probably you would say okay because I think you should change to 8-6 or 7-7, depend. The last one doesn't really matter, right? It should be 7-7 because at the end probably they split equally, right? Or we can make X6 the same, right? But anyway, it's just like choosing as a dominant strategy. So player two is selfish. So 7-7 doesn't really matter anyway. But you will see that, I mean, if you do backward induction, it's always you choose S, right? Because you always get $2 more than others, right? Then you always, okay, why don't we just stop whatever, right? Because no matter, actually in this case, no matter what player two do, player one will choose S, right? And player, given that, that's why everything will S at the end, right? From the beginning, right? Backward induction. There's only outcome is choosing asset. But the question is it reasonable, right? Because this is Pareto inferior, right? It's no matter what. I mean, any outcome actually at the end, actually in the save for the second one, anything beside the second outcome, right, is much better for everyone. So why we predict the first one there, right? You would be thinking, okay, let's wait a little bit before you do it, right? So that is the 割韭菜游戏, right? So basically, you don't want to so early to 割韭菜, right? You want to wait until a little bit, right? You just good, then it's nothing left over, right? You wait until a little bit, wait until it grow, and then you go, right? So the question is who go first to get more, right? So this is a 割韭菜. That's why I call it 割韭菜 game, right? There's two guys try to bump the money to the market, right? Bump the stock price up, right? Whoever go first get $2 more, right? You don't go at the very beginning, right? Right. So you wait until a little bit bubble comes out and then you go, right? So that is exactly the question. And you can see that in the experiment, right? You often need people would expect you don't actually people wait for second round or third round actually to go, right? So wait a little bit, right? Especially when this game is done many times, right? You don't, I mean, you would not see at the end of the game, right? But at least you will see people collaborate. Some early rounds can collaborate. Okay, so that means that when you have error induction, right, and you have expect people are super selfish and they're super rational, you see this, right, and you will see somewhere in the middle will be the outcome. So actually, this kind of experiment question the validity of subgame perfect equilibrium. Well, good subgame perfect is very unique outcome, right? But it is not probably there's something missing in the model, right? Either we assume people can compute this, right? Or maybe we actually do not do barrier reduction so perfectly. Maybe we are seeing something like this is a good outcome. We may are betting one of the outcome will be there, right? So that is that's the case. Okay. Now let's look at the other game that is more common, and this is the game that we engage usually is the simultaneous move allow. All right, as I said, the example will be there's a two-stage game, usually multi-stage game. The first stage will be, say, upstream firm move, and second stage a downstream move, right? Or in the financial market, right? The informed investor do investment first, and those uninformed will do the second one. This is also often seen in the model, right? Or the other way around, right? Or these are the multiple round, right? Or look at hedge fund, right? The multiple round of financing, right? You can decide which round to enter and how much, right? These are all the all possible application, and it's so common. So let's see. And that is indeed the game is not too much different. Okay, the only difference is who move now is not a function, it's a set. Right, the P function is no longer mapped to n, but is a power set of n, right? Because it's not pointing at one guy, but a subset of guys. And then what can be done now is not an element A, but rather the product set of all possible agents that can move now, right? So there's only two differences, right? The difference is who can move at a point of time given the history is more than one. That means the history will have to include the action of everyone moves, right? And everything the same, right? So that is very simple. And actually, we can represent the game that we have studied in the last chapter, right? The simultaneous move game in the game tree, right? In that case, the players are 1 and 2, right? The history now actually simple. Either has none have moved or both have moved, right? There's no T and H there, so T and H is gone. And these are all terminal nodes. And they move together. And here is a set in the null history. Two guys were there. It's a set, right? So player one, what? Someone control my computer? Or I have superpower to move it. But anyway, H and tail, head and tail for null history. Player two head and tail, right? So it's not contagion, right? So basically just much more simple, right? But the action set become this one, right? The history is and much simpler, right? The payoff is just what are the possible outcome and what are the payoffs, right? So in that case, then we can draw a tree diagram, okay? Still represent the game, but we will introduce a new concept called information set. Information set is telling me that if the player are included in this node, okay, connect the history, means that the player cannot distinguish where he is, okay? And the subgame have to be the case that where we cannot cut through information set, okay? So let's see the example like this one. So in this game, okay, player one decide head or tail. The difference is the information set here, the red one, which tell me this two history. Player two does not know when he makes decision. He has no idea whether H or tail has been chosen by player one. Okay, so that means that his strategy must be the same, head or tail, cannot be different there, right? If it's different, they know he is. So this is identical to him. He has to either choose head or tail. Okay, and in this game, there's only one subgame. There's a whole game because this is not a game by itself, right? Because when you cut here, right, this is not a game, complete game by itself, right? So from here, there's no history there, right? Has to, because we said subgame, right? It must be start from here. You erase everything history, its own game, right? But here you cannot actually erase the history. You actually don't know where it is. You can't start from here because you don't know where we are, so you can't start from here. Okay. So let's have a 3 minutes to ask ourselves, what has strategy said for, don't look at the answer. What has strategy said for player 1 and player 2? Okay. And how many sub-games in this game? Very simple. I just give you 1 minute. You can do it. We'll tell the answer. Try not to look at the answer, please. Hope that's okay. We may start now. So strategy of 1 is very simple. I just move in 2 cases. Okay. Either A, B, C, and F and G, right? Because you don't know, F and G have to choose at the same time. A, B, C, you can choose. So it's A, B, C times F, G, right? So player 1 will be A, B, C, because he can choose A, B, or C, right? It's allowed it. Okay. And the cross product with F and G, because player 1 doesn't know where he is. It's either F or G. And what is player 2? Player 2 is either D, E, right? Can be chosen, and H, I, J. D and E, cross product of H, I, J, right? So that would be 6 outcome for each, 6 strategy for each, right? For every D, you can choose H, I, J. For E, also H, I, J. So 2 times 3. Okay, 6 strategy for each one. So next one is to check the subgame. So player 2 can choose whatever in this right-hand corner. So this is one subgame. Okay, because from now on, player 2, if B is chosen, given history B, this is the game by itself. Okay, there's nothing depend on what happened in the other thing. It's a game by itself. Okay, and here 1 doesn't know he's here, so there's no history. The player 1 actually will know is here. It's not a complete thing. So go back to this one. This is a subgame. Why? Because from that on, player 2, after A is chosen, you cut it off, the history, forget about what had been done. It's there, right? When here, you cannot forget because you don't know where's here, right? So you can't really forget. And that means that there are 3 in total. There's 2 red one and the whole game. So total 3 games. Okay. So if you want to find subgame perfect equilibrium in this context, you have to find Nash equilibrium this game, Nash equilibrium this game, and Nash equilibrium in the overall game, right? You can have to solve this model. Okay, rather complicated, but this is the main concept there. Is that okay? I hope you know how to solve this. Okay, is there? Okay, there's a 3 different game. The whole game, subgame after A, subgame after B. Now we just go to other example. The prediction game is more fun. Okay. Before the incumbent and entrant, when they come in, it's just fight and accommodate. Okay, that is make it simple. But now let us focus on the case where there are two segments of the market. Okay, one is small, one is large. Okay? Small is a niche market. So if they both choose the same market, they fight the worst outcome, right? If they focus on one is small, one is large, right? The incumbent is still earning some money, one negative one, right? If they both choose small, then actually they would lose a lot of money, right? If the incumbent choose large, the entrant choose small, then the small market, the niche market earns some money, but the large market you still would lose some money. So this is the payoff structure. Is that okay? The exact number doesn't matter, but just to illustrate the idea there, right? The number. Right. So if you solve this game, we will focus on the subgame, right? Because the barrier induction, the same idea, right? You just look at the subgame. This is focus on this game and see what is the outcome first, and then put the next agreement here and solve it, right? The barrier induction idea. Okay, we don't have to worry about that. Okay, look at the last game. Okay, you try to rewrite it in the normal form, which is here. Then the red one is the next equilibrium. Why? Look at this large and small. Player one don't and entrant don't want to deviate. The incumbent don't want to deviate. So there's a next equilibrium. You check this guy. Does he want to go down? No. Does the incumbent want to go to small? No. You can check the other one. This is not the case, right? So only this red one. So there are two possible candidates, right, for the whole game. So you have to choose. You have to try everyone, right? So that is how we're doing that. Okay, you can see the slide is I would choose the small and large, right? Large and small and large in different game. Okay. Under large and small, and this become 1 negative 1. Then player one will choose the entrant with the 0 or 1, right? In that case, 1 is going to be working, right? So basically, it's the newcomer come in on the large market, the existing guy focus on a small niche market, right? That would be the equilibrium. Okay. And in the other case is actually the entrant stay out. Okay. And when it's in, it's going to be there. Okay. But actually, remember, this doesn't realize, right? The outcome in here, this equilibrium, okay? Equilibrium like this, right? But do note that what is equilibrium outcome here? Look at this equilibrium. Equilibrium outcome in this context is actually entrant doesn't get in. In this end, outcome actually gets in, right? So why it's not getting in was economic reasoning there, right? It's saying that the entrant expected actually the guy actually would come in with a fight, right? Then he occupy the large market. When they come in, they will get the niche market is not going to worth coming, right? But in this case, actually why he come in, because they expect the incumbent actually focus on small market, then he can earn some money there. Right? In that case, it's okay to get in to earn some profit there. And which one's going to be credible? I don't know. At least in the equilibrium concept we do, it's not clear which one will realize. Okay? So the question will go again is, which one is more likely, right? If you ask me, right? There's a total equilibrium. Of course, usually the paper will stop here, and then that's the end. We say, okay, nice, we have two equilibrium, right? And two answers to this question. One is your model is not complete, right? There may be something missing, right? So if add something there, then probably the model will be resolved as a unique equilibrium. That is usually one way to go out. Second is sometimes you can't really add the model because the model has been well defined. Someone using the literature, you can't change it. So you try to argue that which one is more possible. What do you think? What is more possible? What do you think is more possible? The question in IO, right? How to deter entrant. You look at IO textbook, they will tell you that why the incumbent will move the second. He's this guy there, right? If he's able to convince people that he actually will choose large, right? Then the incumbent, the new entrant will either not enter. Right? There's some way that I can convince people I'm crazy, or I'm convinced that I focus on large market, right? Which is reasonable, right? Then stay out, right? No one to come in. So that's why very often we see a lot of incumbent actually invest in a lot on unnecessary production capacity, saying that if you come in, I flood the market, or they focus on a very profitable segment of the market. If you come in, you don't want to fight for me. Right? So it's able to commit, then that is okay, right? That's why a lot of country, right, do military exercise, show the muscle, right, to avoid get trouble, right? Look at the nature in the world, right? Why we would see animal getting a camouflage, right, pretending very strong, right? That is the idea. Right, so that is the reason that to avoid conflict, right? So come in, you have bad outcome, so don't come in, right? So that means more credible, right? When you come in, then it's not going to work, so rather you stay out. Okay. So let's focus on this. Since we are in the business school, so this is one of the, I guess, besides Conrad and Bertrand, the third one that actually is a most cited competition model will be Stackelberg, which means that one firm moves first, the other firm moves later, and usually the leader moves first, because this is different from the patching managed games, which you have second mover advantage. And in many scenarios, we have first mover advantage, right? Remember the model we have is if the incumbent actually can choose big market, a small market, he will choose a large market, and the entrant actually don't come in, right? So the timing is very important in your model, right? Because you would think that the incumbent actually has a advantage, you can choose first. Okay, depends on scenario, but that's the case. So in this case, we consider a case where same as Conrad, right? Linear demand, constant marginal cost, no fixed cost, right? It's C and symmetric, right? The profits like this, right? This is a standard model we have. And we're asking, okay, firm one actually move first. Okay. Then firm two will choose the quantity after looking at what firm one have done. What is the outcome there? Okay, do note that firm two strategy is not a number, but it's a function, which said if firm one produce 10, firm two produce 1. If firm one produce 8, firm produce 1. So it's a function, right? For every production level of firm one, you have to tell me firm two. So it's an infinite strategy, right? A strategy has infinite dimension, right? Before it's just a number, but now it's a number for every number that player one have chosen. So it's a more complicated, right? Because firm one is choosing a strategy, but firm two is choosing a function. So how possibly we can solve this model, right? Because it's complicated, right? How can we choose a function, right? Right, because firm two is choosing a function, right? But luckily, we only focus on subgame perfect Nash equilibrium. We can use Bell induction. Then our life is easier, right? Because Bell induction means that we fix firm one's production and we solve the model, right? That means that we are looking at, suppose firm one is choosing Q1, which is given, the parameter of the model for the firm two, right? So firm two is choosing maximize this profit, considering Q1 is constant. Remember, firm two is choosing infinite many problem, okay? But each problem Q1 is fixed. Okay, but because the structure of the model is similar for every model, so once you solve one model, then you solve all the model. Right? Do you know that firm 2 we are writing is solving a class of problems, right? Because for every Q1 chosen, this is a problem. And the problem are the same or so similar, you only solve once, right? For every Q1, this is what Q2 is doing. So this is the best response function. So whatever Q1 have chosen, Q2 will choose in this way. Okay. So do note that this is a function. So it's a infinite choices there, right? For every Q1, we have this. Okay. Of course, for this to be reasonable, Q1 is between 0 to A minus C, right? If Q1 is more than A minus C, then it will be 0. The corner solution will appear. Okay. So that would be the thing. But Bell induction tells us this is natural equilibrium outcome, and you put it back to the first stage. Okay, that's how you solve it. So you will solve the optimal choice of firm 1 by substituting Bell induction. You substitute what happened in the optimal thing in the firm 2 would do, right? Which is this guy, and you solve it out. This will be the solution. So it's a little bit convoluted, right? You solve it for the firm 1. So for source given firm 1's choice, you solve for the firm 2 optimal. You put the firm 2 optimal response back to the first stage. And once you solve it out, you go back to firm 2, then you figure out the equilibrium outcome. Okay. Do note that the equilibrium is firm 1 choose this, firm 2 choose this guy. The equilibrium is firm 1 choose A minus 0/2, and firm 2, this is the equilibrium. Remember, equilibrium is strategy profile. So it must be what firm 1 do, and firm 2 will tell for all scenario what is going to be done. Okay? Do you know that? And at the end of the day, what firm 2 done equilibrium is equilibrium outcome. Is that clear? Have to be very careful. What is equilibrium outcome and equilibrium strategy profile? Equilibrium strategy is just this function and this one. Okay? You have to remember equilibrium is to specify all possible strategy, right? It's not the, but of course, the equilibrium outcome will be firm 1 choose this, firm 2 do this. Okay? So that's have to be very careful. Is that clear what we have said? Okay, because have to be specified every possible history. Right? So that's why we need to, the answer should be right in this form. Right? If you ask equilibrium strategy, right? It's possible that Q1 produce 0, right? Or any number, right? Have to be careful here. And the SPNE is to specify all sort of information there. Okay. So as I said, if you know how to solve this model, this type of model, then it can go very far. Right. And I can safely say that, I mean, at least 5 to 6 papers are written is only based on these concepts. Right? You don't really need to go very far. I mean, because even this, if you do it right, then you can go a very long way. Okay. But I mean, even it looks very simple, right? If you have many stages, it can go crazy. I mean, even though it depends on, because remember it's a function of function of function, right? Because each stage is a function. So it can be very complicated already. Now, the next is I want to talk about a special type of dynamic game. And the first question is, we get the same outcome if you repeat the game twice. So I ask the player to play twice of the same game. And would it change if you change to infinite many? Okay, is finite many, infinite many the same? And turn out to be very different. I mean, as a hint, because we learned that, right, firm in the Bertrand model, right, even though only two firms, right, they compete in price is very normal. Why you would see the Bertrand model tell all the firm would not earn any profit, right? Doesn't make sense, right? I mean, and we know that firm actually compete in prices, right? And the way that they can collude, right, implicitly or explicitly, right? They will figure out one way to collaborate, right? And would it change, right? Can they collaborate, right? Because collaborate and earn more surplus, right? So is it way to avoid coordination failure, right? Can they achieve better outcome, right? Just like battle of sexes, right? Can it be the case where on Monday they go to football, on Tuesday they go to a drama, I don't know, movie or whatever, right? And they take turns. Is it better than the other way around, right? So is there any way that these would make sense? Okay, and I have to say that this repeated game is a large literature, so even there's a single textbook focused on repeated game, say 600 pages textbook to be put on them. So we can't really do justice on this one, and this is very technical subjects, especially involve infinity. So basically, all these things are the math problem become more or less. But don't worry, we will just only scratch the surface, give you some idea how the main model is. If you want to go further, I mean, there's a textbook already you can look at. But this become recently a lot of paper about the contract theory would work on the models, right? Because of the when you look at contract, if there's a court can enforce it, there's no problem, right? But it's not every contract can be enforced, not everything can be verified. In that case, repeated game will be there. Okay, but anyway, let's see this example. We know it very well. It's present dynamic game, right? Look at this outcome. DD is only Nash equilibrium, it's only dominant solvable, right? But we know that 4 CC is Pareto efficient, right? But everybody want to deviate from that, right? So the question is, suppose we play this game twice, right? And then when we trade twice, what is the payoff? We add up the two payoff in two stage with some discount factor if we want to, right? By delta, right? Suppose you have CC in the first round, CC in the second round the payoff will be 4 plus 4 delta. So the second round will be have delta, right? So in that case, right, you discount the future by delta because you make the decision right now. So the question would be, okay, if we repeat 2 times, can we sustain the collaboration? The answer is no. Okay, because backward induction. Because every time look at the last round, you would defect. Given that you would defect second round, why I would want to collaborate? The only thing you can left is this defect, right? Because I look at the last round, what are you going to do? You're going to defect. So first round, there's no reason to collaborate. Just defect, right? Backward induction tell us that's over. All right. If you know that from the last round, you're going to be the cheater, then why I'm going to be a good guy at the beginning, right? You see through it, right? At the end, you know, okay, it's not going to work. So why bother? Okay. So turn out that, well, we don't really like it, right? Because we know from experiment, we know a lot of things that actually can collaborate, okay? So the question is it possible to collaborate, get CC with collaboration or cooperation if we play this game forever, okay? If there's no end, there's no explicit deadline, then it's 1 minute forever, right? Forever in this context, actually you can consider as the case where we will envision the world that would end with probably 1 minus delta, right? Because you discount the future as a delta, right? So you consider the world will end, everyone dies with 1 minus delta, that there's still payoff from the future, right? So they will engage in this game with probably 1 minus delta. Okay? And you add all the payoff, that will be, we consider infinite game, right? So forever doesn't mean that they actually have infinite life. It's just saying that, okay, they can't envision that when will be deadline, right? It's unclear when we end, right? So that is actually sometimes you said Deng Xiaoping is very smart, right? When you say when they take over Hong Kong, what he said, 15 years don't change, right? Didn't say what happened after 15 years, right? It's unknown, right? It's a contract that has undefined deadline, so it can work, right? If he said, if the game theory, he said after 15 years, then everything become communist, right? Everything will be state-owned. Then what happened is at the last period, people will sell all the assets, right? By reduction, right? If you know 15 years, everything go back to the government. What happened is in the 50 years, they will sell everything, right? And then 49 will sell everything, and then by reduction, and everyone will sell everything, right? But he didn't say, what happened. So people think it will continue, then it's okay, right? That is same for every contract we see. That's in the marriage contract. It doesn't specify when it ends, right? You envision, for example, you envision that next year we'll get divorced, right? Then the wealth will be divided, right? You get the car, I get the house, or whatever, right? In that case, okay, then you know immediately the day before the end of marriage, then you just sell the thing and grab the money, right? And then you know that the last day you do that, then you will do it before the day before the last day, right? But by reduction, you kind of marriage, right? Or you in the very beginning you just hide your wealth, right? But that is the idea, right? Because we don't know when would happen, so that's why we can sustain. So that's the idea here. So how to sustain this is by the following. Okay, it's saying that we call the trigger strategy. Trigger means that we press a button, something trigger. Okay, trigger means the something happened, you will press a button. Okay, panic button. So what we do is every time if we have been in a good outcome, we remain there. Okay, the history has been cooperation, we cooperate. Okay, if at a time that, okay, if that's not good, then we will defect. Okay, so and that is the way that will sustain the equilibrium, right? So we will be everyone choose C there, okay, then we will sustain 4. If you defect, they will get 1, right? You get 5 in the beginning, but you get 1 forever, right? So as long as your discount factor is high enough, right? If you remain in the good thing, you get 4, 4, 4, 4, 4, 4, right? If you become a bad guy, you get 5 and get 1, 1 forever, right? So basically, just compare these two, right? It's 4, 4, 4, 4 forever, and 5, 1, 1 forever, right? And you can see as long as discount factor is high enough, you get the same, right? So this is how we check the Nash equilibrium, right? So you can check for every period. This is the same problem. The second period, the same idea. You get 4 first, and second period deviate, the same thing. So no matter which period you don't deviate, that's a Nash equilibrium, right? Because you can change, right? So this is a Nash equilibrium, okay? But we need to check subgame perfect Nash equilibrium. That's a little bit slightly more complicated. Because we don't have last stage, we can't use backward induction. What does that mean? That we have to check all possible history that this is still a Nash equilibrium. Okay, so we need to check the following. Okay, what are all possible history? So if the history has been there are only two types of history. One history will be everything is CC so far. The other is some other in CC. Okay? If everything is CC, then we know that when delta is more than 1/4, then it's the case. Okay. And if we have outcome that are than CC, right? Then equilibrium dictator is DED, which is net equilibrium, which we don't need to check because it's net equilibrium already, right? So as long as delta more than 1/4, then this is a subgame perfect Nash equilibrium. Okay, so do note that the checking of the Nash equilibrium subgame Nash equilibrium are different, right? Any just need to check. Is there any other strategy that can improve, right? So we only check along the equilibrium path, right? Along the path that actually there, right? Because there's a, but subgame perfect have to look at all history, especially this guy, right? This not appear in equilibrium, right? Need to change it. Okay. Now, what does that mean? It means that what we said is the common wisdom, the marriage, right? If you want someone disloyal, then you will divorce, right? 就一次不忠，百次不容，对吧? That is what it means, right? Just immediately you will just get away, right? So because you figure out that is not good, right? That's a disloyalty, then you just punish forever. There's only way that you can sustain collaboration, right? So or something in more local thing, more modern thing is 绿帽不怕戴，最重要脱得快，就是 it's the same idea, right? Is there's something wrong, you just punish, right? Then there's only way that can sustain collaboration. It's not about whether you're cruel or what, right? But you have to deter, then you have to be not forgiving, right? Just go there, that is easier. Of course, there's some way you can forgive, but you don't go over there. But this is the way that you go, right? Not forgiving. Is a good way to sustain collaboration as long as you care about the future, right? So yes. Any question? This part is a little bit complicated because you have to check all possible history that your strategy will work, because that is what subgame perfect means. And you can't use parallel induction. So this part is way more complicated than usual. Okay, but if you look at the application, many of the time they variant of personal dynamic, so shouldn't be too difficult. Oh, because if under this outcome, what the strategy would player do? Under not CC, then you would choose D forever. I choose D forever. If you choose D forever, what I'm going to do, no matter what I do, you choose D, right? The best thing I do, choose D. So that is the idea. Yeah, because when the history is not CC, right? According to the strategy, is trigger, right? So no matter what you have done, as long as not collaborate, then you will be choosing D forever. Given that you choose D forever, there's no way I can escape from this black hole. So the only thing I can do is D here. Okay, I cannot go back. There's no way I can escape from that, because we open the path upon no return, right? Because we get through this, we end up in the black hole. Once there, no one can escape. Okay. But if you check Nash equilibrium, we don't need to check that, right? Because it's off equilibrium, right? Only check along the equilibrium what happened, right? So that would be the case of slightly complicated. I mean, looks slightly troublesome. Okay. So let's have a break of 15 minutes. After the break, we talk about some of the little bit more subtle issue. If you expand the game a little bit, actually we can do something more fun. Okay, but we will talk about that later after the break. Okay, let's resume 14:35. take some rest and walk around, and then we'll come back in 15 minutes time. So let's continue. So this is the last example we will look at, and then we go to the formal model of repeated game. So probably you will see if we have infinite repeated game, then we can sustain collaboration. So one of the other way thing about this is, well, maybe we can make some modification of the game, right? We open up, when we repeat something, there may be something open up, right? So for example, if we have the same game for C and D, but we have the option called B. I don't know what B is, but maybe B is, I don't know, they will get 3 and 3, okay? It's not better than C, but B and B is there, okay? And you can see this B.B. is actually a Nash equilibrium, right? And they can do something, right? At least it's better than 1-1. 3-3 is not worry about it. Can be 2-2 or can be anything, okay? And turn out that if that's the case, okay, you can sustain CC in equilibrium in the first stage and BB in the second stage. How? That is what we call carrot and stick. Okay, how we do that? So if someone deviate from the first stage, getting 5, okay, it can be punished by, okay, if this is the case, I will go to 1. If you are not short-sighted, I give you 3. So if you do well, okay, if everyone would follow, we'll go to B, maybe bath, right? Maybe go to have fun, right? B, right? Beer, maybe go to beer, right? They go to beer, right? And they enjoy, right? And if they didn't follow, they're short-sighted, they will go to D. Okay. So this is again perfect Nash equilibrium. Why? Because second stage BB is a Nash equilibrium to check, right? And then you can check deviation, give you the payoff of 5 + 1, 6. There's no discounting. Compared to 3 + 4, 7, right? So as long as, right, 7 is better than 6, then, right, then this is the way you can sustain, right? So that means that if you are able to create something, okay, especially the second stage, that you can reward, right? And that is the way to go, right? That is actually institution, the problem. That is how society maintain their outcome, maintain their collaboration, right? If you do well, right, then after you go out the jail, then you have some money, right? We don't go to, there's some reward from the society that reward you, right? That's why you engage something crazy, right? The trust society, right? They would do that, right? That is how they sustain with the institution, and then we believe this is okay to be there, right? If they're not, then you get punished, right? So that is how a lot of institution, right, can sustain long-run collaboration, right, by rewarding people who follow the institution strict rule, right? Say for example, right? Why are you here still studying, right? Why don't you go to your room and watch TikTok, right? Or watch a Little Red Book, right? Why are you here, right? Because if you deviate, right, go to here, then you get punishment, right? You will get a F grade from the class, right? If we do it, then you will get a good outcome, good grade for me, right? So that is kind of sustainable, right? Because you would tempt it to be go away, right? So that's how we can sustain good thing. Right. So that's why, for some reason, right, in the marriage problem, right, we have people who get married for any year, they have anniversary, right? And then every 30 years, they have, say, golden, silver marriage and golden anniversary, right? It's kind of like, if you do well, you keep reward you along the way, right? Rather than kind of punish you, right? So like, or in the old days in China, right? If a woman, right, don't get remarried, then they 给她一个金节牌坊, right? The same idea, right? Just give some reward along the way, right? But anyway, that is the institutional structure, how you sustain some collaboration. So let's have a with the game, okay? And the only difference is a normal form game here, A and AU. The only difference is T. Okay? T is telling us that how many rounds it's going to repeat. Okay. And do not that repeat the game is a special type of dynamic game, right? But such that every time you repeat the game, same. Right. So that is the special type of game with the game. And if you repeat it finite number of times, it's finite with game. And then if you go to infinite, it's infinite with the game. And then, as we have mentioned, these two are very different. Okay. Especially when you go to infinity, everything change. One of the thing that you might think that, why don't we just solve for the finite t and t take infinity, will it be done? In general, they are not the same thing. And usually when you t go to infinity, the set of equilibria you also usually expand a lot. Okay, just remember when we have precision dynamic, right? Any finite t only have one outcome. But when you go to infinity, then actually a lot of outcome is possible. Okay, so that means that you can't really go to the finite and take infinity. So they're very different animals. And sometimes that actually the outcome in the finite with the game may not be the same, may not even in the same set. But anyway, history is simple. It's just what has been done in the past, right? The strategy is or the action, right? Depend on what the history, what the action, right? The strategy will be just what action is possible, right? The strategy profile is just adding every player strategy up. So this nothing new there. Okay. The only thing have to be careful is we define what we call behavioral strategy. Okay, which is saying that at this point of time, what strategy can be done. Okay, so that is a little bit abuse of notation or abuse of the language. So we define one thing is called the path. Okay. Path generated from the action, which means that what are the strategy, right? Would it induce what kind of outcome being chosen, right? According to different, say, precision dynamic, according to this particular strategy, the path may be CC, 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 right? So this is the path, is like the history generated from that, okay? And this is what we call path generated from it after the history. Okay, so that is what is said, okay? And the payoff will be simply, we will focus on discount factor, additive discount. You just look at every single point of time and you discount it, okay? So that would be the idea, because there's a payoff for every period, okay? So that's why you calculate it in this way. So there's abuse notation, right? Because U should be only defined for the action, right? For each stage action, but with this abuse notation usually also apply to the set of the actions. So Nash equilibrium is nothing new, right? But just trying to see if I change my strategy, right? It's not going to be profitable, that is Nash equilibrium. We do this in the personal dynamic, right? We just check holding other guys are collaborating, then is I still do collaboration, right? So that is a Nash equilibrium, okay? Do note that we just holding other guys strategy the same, okay? That means that we only check along the equilibrium path, okay? A particular path, we just look at every point of time along the path whether anyone will deviate. That is only me to check. And subgame perfect equilibrium is way more complicated because you have to check, okay, not just for the current history, but for all possible history, okay, that potentially can be generated by different strategy you choose, right? Because potentially you choose different strategy in this stage can lead to different game being played, right? We generate different paths, right? So this is very complicated, right? Just like have to check every single history, and you deviate, you can go to other path. So it's a humongous object to check. It's very difficult to check because this is, as we can see, right? Subgame perfect has a little very complicated check, right? For every possible history. And when DVA actually can go to very complicated stuff. Okay. And luckily, in the problem that we care, we can use what we call one period deviation principle. That actually is saying that when we look at subgame perfect Nash equilibrium, we don't need to consider a very complicated deviation strategy. We need to check in this period whether I deviate, then it's done. I don't need to consider a multi-period deviation plan. It need not be very complicated. I just check period by period. In this period, do I want to deviate? Okay. I don't need to check the strategy that I deviate in the third period, fifth period, sixth period, and remain the same. Do I need to? No. I just need to check in this period, I just deviate from the plan, okay? And that's done, okay? So that is the result from operation research, okay? So that is only need to check, okay? So this is the first theorem we have, is very simple. If the stage game has a unique Nash equilibrium, that it will continue to do so if you only repeat finite number of times. That is barrier reduction, right? Look at barrier reduction last stage. This is what had been done, and then you continue to do. So that is the result we have, okay? But actually, it means that if you have more than one Nash equilibrium, okay, then the example we have is things that is not equilibrium can be supported, okay? So that means that if the game is much richer, so you can support something that is not Nash equilibrium in one round. So that good thing is like, okay, Nash equilibrium may not be the best thing to do to analyze, right? Because to know exactly how the game is being played. Is it played once, twice, or 3 times? Otherwise, we don't know what's going to do, right? Suppose we look at Bertrand competition, right? It's modified version, right? If we think that actually they play the pricing game for twice or 3 times, right? They may meet tomorrow again, they play the game again. It need not be they compete to marginal cost, right? If they think that actually there's a more than one equilibrium that can be there, right? Because they repeat the game can be basically more complicated, right? In that case, that we're able to sustain something that is not in equilibrium in the original setting, okay? So that is very important, right? Because that means that okay, the game may not have something that you want to predict, right? But if you allow they play twice, then you can predict something that is not there if you just analyze in one period. Okay. And especially for environment, right, is very easy to think percent dynamic. Okay, that model problem solved, right? No matter how many times you repeat, right? But if you allow ourselves to make more choices, then actually you can sustain something good. All right, so that is something new here, right? Allowing some strategic freedom actually can allow something desirable can comes out. All right. So in this case, right, you can see that is the value of vision or value of the leader, right? Maybe now the leader institution tell you that we can reach here, right? There's something not so desirable, but just telling you that there exists some good outcome, right? Then we can collaborate, right? And that's why people would think what Elon Musk is great is because he point out that, okay, we can go to Mars, although it's not as good as the thing, but we go to Mars, we get free, then we can sustain good outcome now, right? Because if say, okay, if we don't good thing, then we are not going to Mars, right? We stay in the Earth, we all die, right? But if he say, okay, it's possible that we go to Mars, right? Open up the option there, then we can sustain collaboration on Earth. Okay, so that would be something that that you can think about, right? And the leader or the vision or the good people can point out this is the way you can avoid trouble. Okay, and of course, talk about with the game, the most important thing is fog theorem. Okay, fog theorem means something very simple. Okay? It means that anything is possible, basically. Unfortunately, what it means is precisely means anything that is best than Nash equilibrium is doable, right? Because precision dynamic is already the worst case scenario, right? And we're just saying that anything in this particular example, right? The statement is actually said the following. Okay. The example is like this, right? 4411, right? It said any equilibrium payoff that's more than 1 strictly can be sustained as subcapital equilibrium. So you can sustain the payoff on average is 3, any number is fine. Okay, any number 3, 4, 4, 3, 3.5, 3.5 is doable. Okay. So as long as you allow people patient enough. Okay. So as we can see, precision dynamic, CC is sustained. Okay. When the delta is more than one quarter. Okay. Anything the Pareto dominate, Nash equilibrium. Okay. You give me subcapital Nash equilibrium, everything Pareto dominate that can be sustained by using what we call this trigger strategy, which means that I demand that this outcome will be realized. If I'm not satisfied, we go to the DD is a punishment for everyone. So that can be sustained, right? The same as precision dynamic idea, right? So basically just generalization of precision dynamic. So I will propose there's some outcome which is not Nash equilibrium, right? Any payoff you propose, that's fine. And then you say, okay, if this is not according to what we propose, we go to DD forever. Okay, DD is the way to threaten people out. Okay, and people are patient enough, they think DD is worse, so they can sustain whatever you think. So that's called the fog theorem. So you may think this is positive result, right? But some people think it's negative result, right? Because if everything is possible, the prediction power is nothing, right? But at least you can show that if people are patient, we can sustain collaboration or collusion, if you like. Okay. So although it's a negative result, that means that in the subsequent literature, they will study some changes to the model so that it may not be possible to obtain the nice result, right? Just like contract theory. If your time we cover that, then you will see if everything is nice, is complete information, then everything's verifiable, you can solve the problem easily. So we introduce some constraint to introduce some inefficiency, then we study those, right? Just like we learned the first welfare theorem and second welfare theorem. Market is so good, right? Then we are done, but we know that we are not done yet because there are many things we didn't consider. Or if you learn from finance people, there's an MM theory, right? Everything doesn't really matter whether the financing decision of the firm, right? Same the value would result, but we know that things doesn't hold, right? There's a lot of complication there. So anyway, now we study the model of firms compete in Connaught, okay? And we'll do a repeated game here, okay? So immediately you will think, okay, why we care? Why don't we have a Fock theorem? If they're patient enough, they can sustain collusion, right? They collude at monopoly and split the monopoly profit. That's the best, right? But here I would tell you that, okay, that have to be saying they have to have the delta, the discount factor is high enough, right? What happens is not high enough, right? That is what we try to do. We will fully characterize the model by looking at different patients level. If people are not patient, 0 patients, then what we expect is Connaught outcome, right? When people enough patient, then we will split the monopoly, right? That is the 2 prediction we have, right? If people only care about now, delta is 0, right? They don't care about the future, right? So that only care about today, that is Connaught, right? And if they care something about the future a lot, sufficiently patient, then we have division of monopoly rent, okay? Now then, in the intermediate step, a little bit more complicated, that's what we do, okay? So we'll finish this, and then that's the end for today, because I think that will be complicated enough, and then we'll consume all the time. And then we'll left the application of price collusion in the next class. So here we have a Connaught duopoly. It's very simple. 2 firm, Q1, Q2, and the market price is same linear, P minus Q, marginal cost C, no fixed cost, right? So you can easily solve for the Connaught Nash equilibrium. By now, you should know how to solve. Probably you'll see the assignment later once we finish this chapter. And you can figure out this is Nash equilibrium gives you this one, 1/3 of A minus C, and the price will be like this, okay? And then you can also solve for the monopoly price quantity, which if only single firm there, this is the outcome, okay? So as I said, if firms don't care about the future, this is what we expect. If the Fock theorem was said this is possible, right? If they collude, they will split this, okay? They will jointly produce as if they are monopoly, right? Because in monopoly, the best case, right? You can achieve, and then you can split the monopoly is the best. Now consider the case where firms are extremely patient. Okay, of course, we tell you what the extreme patient means. But in that case, if patient enough, the firms would be doing is they will split the market as a monopoly. So every firm will produce QL/2, okay? And the trigger strategy set is if they have been collaborating, they continue collaboration. If not, then they go to Connaught outcome, right? That's trigger strategy, okay? By Fock theorem, we know that this is doable, right? The only thing we need to know is what delta. What delta, okay? So basically, we just reduce the game to personal dynamic, okay? So basically, in this particular case, right, although it's complicated, basically we reduce the personal dynamic like this, right? So they will collaborate, defect, collaborate, defect, right? And under both are collaborate, every firm will get monetary profit over 2. Right, that is the outcome there. Okay, and when they defect, they will do Nash equilibrium. Okay, that will be there's a corner outcome, the Nash equilibrium, right? So the only difficult part is what is the payoff for these two? We have to fill this up, right? Because basically what we do is because trigger strategy, that we can focus on the case where we say prison dynamic game, right? So we need to figure out what are these two entry over this two, the box here. Okay. So we first calculate the monetary profit, right? So this half of that, this is the profit. So we know this number here. Okay. There's nothing new here, just divided by 2. Okay. And this is the profit and NE. Okay. So now we will say what happened when you deviate. Okay. When you deviate, that means that the other guy is still producing monopoly. Right? So you calculate they keep their strategy, keep what they're doing, what's the best you can do. All right, you calculate that payoff. Is that clear? Okay. And you solve the FOC, calculate QD, this is the payoff. Where you defect, this is the gain, right? This is the 5 for prison dynamic, right? You deviate, this is the payoff. Right? So it will be something like this, right? If for firm 1, right, collaborate, this is the payoff. You deviate here, and if you do crazy thing, they will end up into this one, right? So we have the payoff, we have the high there. You can calculate the rest, but I just don't want to. We don't need the calculation. You can calculate all the thing, right? There's no problem. You can calculate profit all the thing. Actually we don't need that. So let's calculate it. What are the profit? Okay. So if you collaborate forever, that will be the payoff, right? It's geometric sum, right? And if you defect, then you get $5, right? That is the thing. Then you will get NE forever. So that's a payoff. And you want the first line better than second one, right? That's only check, right? That's the only thing you can check. You need to check. Okay, this is the case, right? Because when you are in Nash equilibrium, it's already you need check, right? So there's only thing in the check, in order to check Nash equilibrium, right? You check everything on the equilibrium, right? On the equilibrium, this is the thing you check, right? And NE is already equilibrium in the check anyway. So just put the number there, figure out that delta is more than alpha 17. I'm not going to equation by equation. I think that is something simple for a PhD student, right? If you have any question, let me know. I don't want to go over line by line, but that should be something sufficiently simple. You can do it on your own, right? I tell you how to do it already, how to check, right? So that is already tell you the trigger strategy, right? As long as people are patient, this can be sustained. There's nothing new there, just prison dynamic, right? Idea. Okay. Now, what happened if less than 9/17? Okay. So why then what can be done? Then it will economics, look at economic first, is why we can't sustain when the delta is low enough. Because people is very tempting, right, to being a bad guy, right? Because the short-term gain is so large compared to the corner punishment, right? That means that we cannot be colluding at a right level, right? Because we produce too little when we collude, such that the gain of monopoly, right, is so high that when you deviate, the gain is too much. So basically, you reduce the gap between 4 and 5. So basically, what we are doing, to think in this way, is the following. So basically, look at this question, right? The gain for the one period is 1, right? And then 1 forever, right? So because of this gap is so large, and your delta is very low, right? So this 1 in this period is too large, right? So we can't sustain collaboration. So how can we sustain collaboration is to make this smaller, right? To make this smaller, because we control this guy, right? Our agreement is this guy is endogenous, right? We make it smaller so that the gain you can get is not that high, right? Then you can sustain collaboration, okay? And by making this smaller, this also smaller as well, right? So making both of them smaller, then we can sustain. So that is the main idea. Because we can't sustain at the level that monopoly, right? So we just try to do it inefficient, okay? It's inefficient, it's not able to sustain monopoly. We produce a lot, much more in the when we collude, such that if you deviate, then not much gain you can gain, right? Because we produce more than monopoly level, okay? So let's see, we have to calculate how to collude with QC is to be determined, okay? And this QC later you will see depend on delta, okay? How much we can collude depend on how patient we are, right? If you are 0 patients, the QC will be QNE, right? Because not patient, we cannot agree on anything, right? If delta is high enough, QC should be, say, if delta is very close to 9/17, then QC is actually the monopoly level, right? So basically, you should be changing from monopoly level to Nash equilibrium Coulomb level, depending on delta, okay? Later, you will see it's continuous. So under collaboration, everyone produce QC, this is a profit, right? 2 firms produce QC, this is profit. Under NE, this is the profit. There's nothing new here. So that's the idea, right? The precision dynamic 1 is the same, right? So this is the 4, but with this 4 will be, we have to decide what is that one. Now slightly more complicated is to calculate DVA, right? The deviation gain is depend on how much we collude, which is QC. Right, so this is a little bit more complicated. Is this part? Is we have to calculate. We agree on QC. Okay, if you deviate, what you gain? Okay, right? Because QC is no longer a monopoly level, right? It's not before the case it's half a monopoly, but this one will be the number that determined by delta later. Okay, and you deviate. This is the part. You produce this and you put it back. This is the profit. Okay. Okay. Yes. Oh, QD is a choice. You differentiate the Q square. So you have AQ, Q square, QC, QD, QQ, differentiate this square. Or should be Q, I mean, same thing, right? Because D is a choice. And equilibrium require you to get, okay? You get the collaboration forever, you deviate, and then you get next equilibrium. So you compare the three, right? Same as precision dynamic we have, right? You get the collusion forever. Under QC, everyone choose QC forever. You deviate, you get this much, and then you get punishment, right? So this is the same. So this is both firms choose QC. And if the other firm QC, then you choose QD, that's what you get, right? But if you become a bad guy, then you get punished. We get punished forever, okay? So that is how you get it. And you solve this inequality, okay? You figure out QC is equal to this one, okay? As we have hinted, how large and how small we collaborate depend on delta, okay? So if you look at this thing, you take the delta is decreasing in delta as we expect, right? The smaller the delta, the more difficult to collude, and it's decreasing, right? But this decreasing is a decreasing rate, okay? And you can easily check that when delta go to now for 17, you get to the half of the monopoly. When delta go to 0, you get any. So this is what we expect, right? It's easier to look at the graph to convince you this is a case. I think that's easiest, like this, okay? When delta is high enough, we sustain Bob theorem, the best scenario. They split the market as if they're monopoly. If they're not patient enough, okay, they have to sustain a less efficient outcome, right? Because the most efficient for the firm is monopoly, right? They can collude at the right level, they will overproduce a little bit compared to monopoly, right? And if the worst case scenario, they would behave as if they're cannot, right? So that is this shape, right? Because okay, so that would be the model, right? You can see that Bob theorem is very important, right? Because it gives you the result, right? But here I give you the frontier, right? What is possible for the firm, right? This is the best firm best equilibrium. It's like this one, the red one, and depending on this, right? Of course, anything below is already also feasible as well. All right. So that's what we have. Okay. So I think the good part is probably you don't learn in the undergrad is you don't do the red one, right? The blue one is the one undergrad. The fourth film you learn undergrad, that's done. But what happens if less than that is not done? So I think from this class, this is what you learn the red one. And the red one, I think, is more important than the blue one because blue one is we know everyone is patient and it's over. But we know many of the time we're not that patient, right? So that means that we only able to end up with the red one, right? So that's OPEC, right? OPEC means that if people are not patient, then probably end up in something there or pollution problem, right? And environmental problem, right? Because we are not very patient, right? Especially when some in the society, some people are young, some people are old people have no patience, right? Because they will die tomorrow, right? So who cares, right? In that case, right? So only the young society, then they have lot of patience, right? When the society aging, there's a problem, right? They don't really care, right? They die, right? So that is the issue there. Okay, so after next class, we will finish up the rest of the chapter. This very last diagram. Here we show you that the green dot is the corner outcome, okay? And the blue one is the monopoly, the share, okay? And the red one is actually how we progress to the green, depends on how patient they are. If they're super patient, it's blue. And if they're not enough patient, they move slowly to the green one, right? So if they can collude, they go to the blue, but if they're not good enough, they will go to slowly move approach to the green. I think that is a very nice diagram to show you how patients change the possible outcome. If you repeat the corner game, right? If you only have one game, that's green. But if you give them enough patients, they're blue. If not, then they will end up in the upper hand corner. Okay. Okay. So I guess I should stop, and then next time we'll go continue our journey on the rest of the chapter. Okay. So I'll see you next Wednesday. Bye bye. I'll stay around to answer any question you might have.